Hello, I'm Ryan Magnuson.
And I'm Colton Smith, and this is our Neuro 556 and BME.
Yep, BME 556.
This is our project, and it's on Alzheimer's.
So first, we'll give a little background or motivation on why Alzheimer's disease is important and why we decided to study it. So here's just some general facts that are pretty mind-blowing when you look at them. So every 66 seconds, a new person is diagnosed with Alzheimer's disease. It's the 6th leading cause of death in the United States alone. Out of the top 10 top diseases that kill in the United States, it's the only one that cannot be cured, prevented, or slowed. Out of all the dementia cases, it accounts for 60 to 80% in the United States, and it's responsible for 700,000 deaths per year in the United States alone. 236 billion is spent on fighting Alzheimer's disease and dementia, and it kills more than breast cancer and prostate cancer alone. More than 5 million Americans are currently living with the disease, and 1 in 3 seniors will have Alzheimer's disease or another form of dementia. So the human lifespan is increasing. Changes in human longevity illustrate the rapid extension in lifespan that has occurred in the United States over the past 100 years. This is primarily due to the medical breakthroughs that have occurred. The increased longevity is a double-edged sword. Although people are living longer, age-related cognitive alterations are increasingly prevalent. Their extent varies widely among individuals. For many, the alterations are mild and have relatively little impact on the quality of life. But by 2050, the number of people aged 65 and older is going to triple, along with the people with Alzheimer's disease. So currently there's 5.2 million projected with Alzheimer's disease, and this is supposed to triple to 13.8 million by 2050. So just a general overview on the disease. As we mentioned earlier, it's the most common type of dementia. It has no known cure, and the disorder is both irreversible and progressive. It causes cognitive and functional impairments within the individual, and it's characterized by the formation of protein aggregates and the loss of neurons in the cerebral cortex, which we will go much more into detail on this further on in the presentation. It's known to target large-scale brain networks, and specifically those that support the formation of new memories. Most people who get the disease live with an average of 9 years after diagnosis. So some of the symptoms associated with Alzheimer's disease are initially there's short-term memory loss, confusion, irritability and aggression, and mood swings. A lot of the time with the associated memory loss initially, people tend to have trouble with planning and problem solving that starts interfering with their daily tasks. Anything that has to do with numbers and computations or navigation, getting to places, keeping up with busy schedules, just your basic daily tasks begin to be a lot more challenging. There's also known changes in vision, so your brain has trouble processing certain visual things and picking up on contrasts. Then there's also some associated long-term changes, and this is after the disease has progressed and really starts interfering with these basic systems in your brain. So you'll see a lot of more long-term memory deficits. The people will begin to have trouble in conversations, understanding words, remembering names, losing things. They have a lot of lapses in judgment, and with these, the person will become socially withdrawn, and they just slowly, their daily functioning just begins to degrade. So there's 7 main stages of Alzheimer's disease that have been identified, and typically they're identified based on the changes in the person's life because of the disease. So the stage 1 is just normal outward behavior, and typically in this stage, most people don't notice any major changes in the person's behavior. The only way you would be able to notice some changes is in doing some type of brain imaging, such as PET scans, which can reveal that the brain is not functioning optimally. And through these scans, we can diagnose Alzheimer's. Stage 2, there's just very mild changes. as we mentioned earlier, with the short-term memory loss, a lot of times nothing's really noticed, even by doctors. They might miss things, but this is where you'll start to notice very small nuances in the person's behavior, such as forgetting words or misplacing objects. And then we have stage 3, which is characterized as mild decline. This is the point where you'll start noticing some mild changes in the person's behavior and in their thinking and reasoning. Stage 4 is characterized as moderate decline. During this period, this is where you really see deficits in thinking and reasoning. And as each stage progresses, they get more obvious. Stage 5 is moderately severe decline. And this is where it can get a little tricky. In this stage, the person might start to lose track of where they are and what time it is. They might have trouble remembering basic addresses, phone numbers, certain things about their past, such as where they went to school. They can even get confused about what day it is, what season it is, and which clothes to wear. So it might be summer in Arizona and they'll be wearing, winter clothes due to their confusion. Stage 6 is severe decline. As the disease progresses, this is where the people might begin they won't even be able to recognize faces of family members and loved ones. They might mistake certain people for the wrong person. For instance, the person, say a male has it, he might start thinking that his wife is his mother. This is where delusions will start to set in, such as thinking that, say the man's retired, he'll wake up in the morning and think that he has to go straight to work, just like he did, 20 years prior. And then stage 7 is the very severe decline. And typically in this stage, the person needs to be in a special care facility. This is where the most basic abilities and functions, such as eating, walking, and sitting up, will start to fade. This is where the person will need to be fed, they'll need special care, they'll need to be fed with easy-to-swallow food and special drinks, and it's really important during this stage that the person has really good care, because they will not even be able to drink whenever they get thirsty, and without the proper care, they won't even be able to stay hydrated.
So the underlying neuroscience of this Alzheimer's disease is that it's characterized primarily by 3 dramatic abnormalities. The first being brain atrophy, so you're going to see a reduction in the actual the size of the brain and the features of the brain. The second is going to be amyloid plaques. These are going to be really actually noticeable in the end state, or long-term Alzheimer's. And then 3 will be the neurofibrillary tangles. So in a healthy brain, the cerebral cortex is responsible for a multitude of functions, such as language and information processing. The hippocampus, as seen, is... Okay, we're going to read that. So in a healthy brain, as you can see on the left, the cerebral cortex is responsible for a multitude of functions, such as language and information processing. The primary regions that are going to be affected in Alzheimer's are going to be the hippocampus and the prefrontal cortex. With the prefrontal cortex, this area is very important critical for the formation of new memories. In the Alzheimer's brain, the cortex shrivels up, which is going to damage areas involved in thinking, planning, and remembering, while at the same time, the ventricles are going to fill with cerebrospinal fluid, which causes the ventricles to grow larger, which is going to push onto the cortex. And along with that, you're going to have a severe shrinkage of the hippocampus. Plaques and tangles are what affect the performance of the neurons, which eventually causes the neurons to die. So Alzheimer's disease not only affects the communication between neurons, but can also cause them, or enough damage to the neurons to cause them to die. And widespread neuronal death, as you can see over here on the right, is what causes the significant reduction in the brain matter of those with Alzheimer's disease. And that's pretty obvious between this healthy brain and this shrunken Alzheimer's disease brain. And if you take a coronal slice, you can see that the white matter on the healthy brain is intact, whereas in the Alzheimer's disease brain it is severely shrunken. So the image, or the images behind us right here, is an image of a neuron that is showing both plaques and tangles. The plaques are found in the neuropil and can surround dendrites, causing swelling. The tangles are going to be found in the cell body and even in the axon. Here we're looking at sections of the cerebral cortex from the brain with someone who is actually affected with Alzheimer's disease, and as you can see over here, the plaques are going to, the tangles are going to show up as really big dark spots, and the plaques are basically plaque-shaped. So the first thing we're going to talk about here are the amyloid plaques. So what happens here is that the amyloid precursor protein is a transmembrane protein that has known roles in long-term potentiation, cellular adhesion, and is found to have a higher rate of expression during neuronal differentiation. So 3 specific enzymes have been identified that interact with the extracellular portion of the APP molecule, the alpha, the beta, and the gamma secretases. These enzymes cleave the APP protein in specific regions to allow for proper functionings. So normally, in a normal brain, the alpha secretase cleaves the APP molecule in an area that prevents the production of the beta amyloid peptide. This cleavage releases a fragment called S-APP alpha, which is the fragment responsible for neuronal growth and survival. The remaining APP fragment is cleaved by gamma secretase at the end of the beta amyloid segment. So that's in a normal brain. But in an Alzheimer's disease brain, or we'll call this the Alzheimer's disease pathway, the beta secretase cleaves the APP molecule at one end of the beta amyloid peptide, which releases the S-APP beta portion. Gamma secretase then cuts the other side of the beta amyloid protein. After cleavage at both ends, the beta APP is released into the extracellular space and begins to congregate with other proteins. Basically, this is what's going to cause those plaques. The fact that they're going to bind together with each other and create plaques. So the next thing we're going to talk about is the third hallmark of the Alzheimer's disease, which are neurofibrillary tangles. Healthy neurons have internal structures or support structures known as microtubules. These microtubules function to transport nutrients and neurotransmitter vesicles from the cell body down the axon. On these microtubules, there are stabilizing proteins called tau. These tau proteins are normally phosphorylated in healthy neurons, but in Alzheimer's disease, these neurons become hyperphosphorylated. This hyperphosphorylation causes the tau protein to disconnect from the microtubule and begin to form helical filaments with other tau proteins. These helical filaments then go on to form large neurofibrillary tangles. During this process, the microtubule begins to disintegrate, destroy the internal transport network of the axon, and ultimately damage the neuron's ability to communicate with other neurons. Which makes sense because, neurons communicate primarily through the axon, so if you start to have tangles inside of it, you're going to ruin the ability of the neuron to do that, and you're also going to degrade it.
So now that we know the basic physiology behind Alzheimer's disease, we can now shift our focus to a more systems-level approach. We know that Alzheimer's disease targets large-scale memory-related brain networks, but we don't know why it targets them and how this relates to the misfolded proteins that we've seen. A recent study published in the journal Brain, in this study, Mayo Clinic researchers have proposed a special disease model that looks at things from a systems perspective. It views Alzheimer's disease as a complex interaction between large-scale networks and small-scale molecules. The researchers have turned to the field of complex systems to try to answer some of these questions. The model that they have proposed supports a system best characterized by cascading network failures. And they use the analogy of the cascading failures seen in power networks, or power grids, triggered by local overloads, which proliferate to downstream nodes, which eventually leads to widespread power outages and system failure.
Researchers at Mayo Clinic took a cohort of 128 Alzheimer's patients and looked at the default mode network, a brain system involved in creating mental constructs and memory tasks. By looking at the default mode network of the brain, the researchers could see how the activity in this region relates to the measures of misfolded proteins. Alzheimer's disease has typically been associated with cognitive impairments such as memory encoding. This inevitably starts to affect other regions of the brain, such as atrophy of the medial temporal lobe, prior to the atrophy of the temporoparietal and frontal regions. And also, you have the metabolic derangements in the posterior cingulate and the lateral temporoparietal regions prior to involving frontal regions. So in this study, the researchers have reported that the systems-level pathology of Alzheimer's disease appears to spread across the default mode network in a cascading network failure that begins with a decline in the most connected regions of the brain, as you can see here at the first A, B, and C, and then you get it progresses to an increase across a posterior ventral to anterior dorsal gradient that causes an increase in activity to compensate. Using this systems level approach, the researchers found 3 very distinctive results. And by the way, I'm going to be referring to the default mode network from now on as the DMN. So first, dysfunction in the medial temporal lobe ventral DMN pathway was correlated with memory deficits. Second, cognitive decline in Alzheimer's disease patients was correlated with increased connectivity between the posterior and ventral DMN. It's interesting to note that the increased connectivity between these regions reflects disease severity as measured by the clinical indicators of impairment. In addition, this increased connectivity is also associated with increased amyloid PET signal and lower hippocampal volume. However, the decrease in connectivity in the posterior DMN is unassociated to amyloid and hippocampal volume. Third, patients carrying the APOE4 allele had a specific relationship with the gene variant to the posterior DMN that could be measured cognitively, or that could be measured in cognitively normal patients before any system or molecular change could be measured. So, the patients with the APOE4 allele had decreased connectivity in the posterior DMN network, or the DMN, before any plaques or tangles had even formed. Upon further measurement, connectivity in the ventral DMN and the connectivity between the posterior and the ventral DMN was normal. As activity in the posterior DMN decreases and activity between the posterior and the ventral DMN increases, there is still no sign of plaques and tangles. However, given enough time, plaques and tangles begin to form due to the aberrant between neocortical network synaptic activity. The noise, over here as you can see the noise that is generated eventually propagates to the hippocampus and increases its burden. What happens now is a positive feedback loop where the neurodegeneration expands to adjacent regions, which lowers the region's ability to handle information, which leads to further degeneration, which is that positive feedback loop. As the hippocampus increases its processing load, it begins to succumb to degeneration itself. Eventually, the level of degeneration in these brain systems shifts in the processing load to the brain's frontal region, which completes this neurodegenerative feedback loop. Eventually, even this system declines as Alzheimer's disease progresses.
So as you see in phase 0 of this diagram right here, you have a decrease in the metabolic activity within the posterior DMN. In phase 1, as you can see, this decreased activity in the posterior DMN causes there to be increased activity between the posterior DMN and the ventral DMN as a compensatory mechanism. This is analogous to what I referred to before with the cascading power grid analogy, where the shifting of processing burden to downstream elements for better performance. It is in phase 2 and 3 where the shift in activity begins to cause degradation of the cellular mechanisms in these systems. This degradation causes a positive feedback loop and ultimately leads to widespread systems failure. These results